Hello everyone. We, John, Gökhan and Yılkut, will present you HDR's vertical axis wind turbines that are suitable for urban areas. Since the Industrial Revolution, the consumption of energy entered period of an exponential increase, and most of the energy demand is provided by nuclear plants and fossil fuels, which led to global warming. Out of clean energy sources, wind energy is traditionally harvested by wind turbines, which need to be very large in order to be viable in terms of efficiency. Therefore, they are built away from settlements and cause a lot of noise. Our purpose in this project is to come up with a small-scale vertical axis wind turbine that is efficient, compact and silent so that they can be commercially viable for a household or a small-scale business used inside cities or towns without being disturbing. Here is our CAD design. We used NASA LS-0417 airfoils, since they provide high efficiency due to its asymmetry according to our research. We decided the airfoil material to be wood thanks to its lightness and affordability. We connected the airfoils with aluminum, and the pole is also made of aluminum. Let's take a closer look to the interior. We put two bearings to the top and bottom. We placed the generator next to the pole and connected it using a belt. Here is the animation of our design. The wind turbine can rotate at 430 RPM under optimum conditions and generate up to 6 watts of power. 3D static analysis. We analyzed the structural strength of the airfoil. The force applied is found by the centrifugal force formula and distributed along the length of the airfoil for a more realistic application. We assumed a rotation of 300 RPM and applied force accordingly. Fixed support was used at connection points to the supporting rods. The results were showing that our design and materials was sufficient for our application. Maximum von Mises stress was 15 megapascals, and our material can withstand 36 megapascals without yielding. 2D CFD analysis. We conducted a CFD analysis of our design on ANSYS under ideal wind conditions, and when the blades are at the design angular velocity. This was implemented on a 2D rectangular domain with one side with the wind velocity, and the rest having far field boundary conditions. The motion of the blades were implemented by a rotating mesh. By seeing the velocity contour at different time steps, we were able to observe how the flow evolves around our design, and the pressure contour has shown us how the lift is generated. Based on these results, we investigated what could be done to increase the lift or how to better convert it to torque. Mathematical model and Matlab analysis. In order to represent an airfoil analytically, we used Joukowsky transformation. We used numerical tools to estimate the parameters to represent the NASA LS-0417 airfoil analytically. Here are the values we found. Although it is not a perfect match, we used this analytical analysis to better understand how the system works and to see how we can improve it. We used potential flow theory to calculate the lift force. Here is the lift force formula, where alpha is the angle of attack and beta is determined by the geometry of the airfoil. However, due to D'Alembert's paradox, drag force is 0. To introduce drag to our system, we used this formula from aerodynamics. Here is the MATLAB simulation. We applied wind at 7 meters per second since that is the average wind velocity in Sarriere. Our system reaches its maximum speed in about 50 seconds. Here are the real-life images of our prototype. Our prototype is a scaled-down version of our CAD design, thus it is more mobile and affordable. We 3D printed the airfoils and connected them to the pole with plastic. We used PVC for our pole. Here is the video of the wind turbine. We could generate up to 17 milliamperes current. Vertical axis wind turbines can be compact, silent yet efficient. They can easily be built inside cities to generate clean energy. They alone may not save our planet, but they can bring us one step closer to a sustainable future. We thank our TAs for their support in this project. Thank you for listening.